to start recording. Okay. So this is the main branches that the course is going to be divided up into. All right, let's get going here. All right, what is statistics? Statistics basically is a way of doing things. It's a science, ladies and gentlemen. Just like any branch of mathematics is a science. Statistics is also a science in that it uses a lot of mathematics, right? The statistical method involves collecting data, first of all, organizing the data by using a table and or maybe using a graph or some other vehicle, and then summarizing our data by using maybe like a graph or a table, and then analysis. Analysis really is at the heart of the statistical method. Subjecting our data to whatever analysis we're going to subject it to, descriptive statistics. Maybe we're going to do some sort of regression analysis or correlation, or maybe we're going to build confidence intervals or do some hypothesis testing, okay? So that's the type of analyses that we will be subjecting our data to. And then obviously, the last but not least important step by far is the almighty conclusion. What conclusion can we draw from our investigation? All right. And the conclusion obviously becomes very important in the branch of statistics known as inferential statistics, where we use a sample from the population to try to infer something about an unknown population parameter. Okay. All right. I already went over the branches of statistics that our course is going to be subdivided into. And data. Data basically consists of numeric or non-numeric entities that we collect. All right. From time to time, ladies and gentlemen, we'll be using variables in this course. Normally, we use the variables X, Y, or Z, but other variables can be used. Now, this course in statistics is not as variable littered as a course in algebra. Okay, so this course is a lot different than a course in algebra. We're not going to be working, intensely with polynomials and solving equations, et cetera, et cetera. But from time to time, we may encounter a variable or two. All right. So the values that the variable can be assigned are called data points or data. All right. And the collection of data constitutes what's called a data set. All right. When we get into probability, our variables will be called random variables in the sense that they can be basically assigned any numeric value by chance. Okay. What's a population? A population basically, okay, consists of all subjects under investigation. All right. For instance, if I was interested in all student majors on a university campus, that would be considered the population. All right, so the population is basically consistent. It's a set consisting of all things that we are interested in investigating. And populations can become very large in some cases. They can number in the hundreds of thousands or even millions of data points. Okay. All right. An example of a population is a census situation where you go out and you basically poll everybody in the population, which is obviously time consuming and or very costly. Okay, so we're going to see the wonder of selecting a sample from a population to do inferential statistics later on in this course here. So, sampling. A sample basically is a smaller subset or subgroup of a population. Very rarely does a sample size equal a population size. Sample sizes are often, most of the time, less than the size of a population. Okay. All right. Now, it's very important how we sample, ladies and gentlemen, because if we do not choose a good representative sample of our population, then our sample will be plagued with bias. Okay. And any result or conclusion we draw from our sample will obviously be condemned to bias. All right, so we have to make sure that when we draw a sample from a population that it is a good representative sample of the entire population. All right. In other words, if I was to poll a sector of the population on a particular political issue, and let's say I just sampled all blue collar workers and left all white collar workers out of the poll or the sample, well, that would be highly biased, okay? Because I'm not sampling, okay, every member or element that represents the population. All right, descriptive statistics will be the first branch of statistics that we get serious with as far as computation is concerned. It basically consists of collecting data, organizing data, and basically doing basic computations from the data. Various descriptive statistics we will be working with will be like means, medians, and modes, quartile values, and percentiles. Those are descriptive statistics. Okay. All right, inferential statistics will be coming later on in this course and will basically occupy our concern for the rest of the course at the end, where basically we reach into a parent population, pull out a sample, and then we use the sample result to try to make an inferential educated guess as to what the population parameter value would be. Why sample? Why not just pull everything in a population? So what's the big deal about sampling? Why do we even waste our time in sampling? If we want to know like a population mean, let's say, why not just pull everybody in the population? Anybody want to weigh in as to the importance of a sample?
Doesn't the sample give you the average of what everybody is?
Well, if you have a good representative sample of your population, then your sample result versus your population result will incur a minimum what is called sampling error, okay? But if you have a biased sample, then there could be a very large error between your sample result versus population result. Basically, why we sample, ladies and gentlemen, is because oftentimes we don't have the time and or the resources to poll everything in a population. Like I said, populations oftentimes can number in the millions of data points, in which case we just don't have the time or the ability to poll everything in a population, in which case we turn our attention to a sample, which is a smaller size data set from the population, which it makes it more manageable to collect, okay? But, ladies and gentlemen, when you draw a sample from a population, along for the ride, inevitably comes something called sampling error, okay? You cannot avoid it entirely. The only way you can eliminate sampling error is to poll the entire population itself. But then we're back to the problem of maybe not having the resources to do so. Okay. That's section 1.1. Section 1.2. Okay, hold on a second. All right. Section 1.2, we are going to identify types of data and identify the measurement level that is used for each variable that we use to assign data. All right. All right, what's a qualitative variable? A qualitative variable is kind of like a categorical variable in the sense that it is non-quantitative, okay? It is non-numeric, right? Qualitative variables might consist of attributes of maybe like cars, okay, or names of months, or names of colors, or names of towns or cities, okay? It's non-numeric, right? Quantitative variables are normally the run-of-the-mill when working with statistics, and those variables almost always involve numeric data, okay? Such as a person's age, height, weight. Those are all quantitative examples of data, right? And obviously, being numeric, we can sort the data, okay? We can maybe draw differences between data points. Maybe ratios between adjacent data points have meaning, et cetera, et cetera. So qualitative variables are non-numeric, quantitative variables are numeric. Oftentimes, our data that we collect and the variables associated with them are either discrete or continuous. What does it mean for a variable to be discrete or for a data set to be discrete? Well, it means, ladies and gentlemen, that the data set can be counted, okay? We can actually count every member or element of the data set. For instance, the number of children in a family, that would be considered a discrete data set, in the sense that you would have maybe 1 child, 2 children, 3 children, 4 children, 5 children, 6 children. There's no such thing as having 1.75 children. Does that make sense? That's an example of a discrete data set. The number of cars in a parking lot. There's no such thing as having a fractional or decimal number of cars in a parking lot. It's either you got no cars, 1 car, 2 cars, 3 cars, 4 cars. This is all examples of discrete data, right? Continuous data or continuous variables basically can take on an infinite number of decimal and or fractional values. For instance, height is considered to be a continuous variable in the sense that, depending upon the accuracy of the measuring equipment, we could maybe measure height out to the maybe 20 decimal places if we had a very accurate scale, in which case there's an infinite number of decimals or fractions we could use for height. That would be considered to be continuous, okay? A digital clock would be analogous to a discrete situation. For instance, on a digital clock, you would see the number 1, and then you would see the number 2, and then the number 3, and then the number 4. You don't see anything in between. An analog clock would be considered to be a continuous type situation, where you can actually see the minute hand sweep a continual swath in between 2 numbers on the face of the clock. That's considered to be continuous. Another example of a continuous data set would be all real numbers between, let's say, 0 and 1. How many real numbers are between 0 and 1? Well, you could have 0.1. You could have 0.100000000001653. You could have 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000
A lot.
A lot. In fact, there's an infinite number. There's a continual swath. There's so many, in fact, you could never, ever enumerate all of them. Okay? That's considered to be continuous. So here's an organization of the type of data we'll work with throughout the course. Qualitative is non-numeric, quantitative is numeric, discrete versus continuous. Which of the following data is considered to be discrete or continuous? Hours of YouTube watched per day. Well, you know, you could consider hours versus what? Minutes and seconds. Do you agree? So this could get very busy. So I would be leaning towards saying this might be what? Kind of continuous, correct? What do you think about the number of books read in a year? Is that discrete or continuous?
Continuous.
What's that?
Discrete.
Probably discrete. I mean, there's no sense in saying that I read 1.65321 of a book. No, it's either you read one book or two books or three books or four books or five books or six books. That's discrete. How about the number of apples on a tree? Discrete or continuous?
Discrete.
That's definitely discrete. There's no such thing as having a fractional apple on the tree. Because if there is, we don't eat it. It's probably defective. We throw it out. All right. How about the weight of a delivery truck? Maybe in pounds or kilograms. Do you think that might be discrete or maybe more continuous?
Continuous.
Yeah, your weigh scale could be very accurate, and it could include many decimals, okay, to give you a very accurate weight of the truck. So that would be probably more of a continuous type situation there. All right. All right, when we do have continuous data, oftentimes we have to consider boundaries, okay, to enclose continuous data within an interval, right? For example, boundary values of maybe a continuous data value of 112.3 might be like between 112 and 2500ths and 112 and 3500ths, okay? 112.3 lies then in, we say, that interval, right? So the bottom line is when we have continuous data, oftentimes we're dealing with intervals, okay? And that will become extremely important when we differentiate between discrete probability distributions versus continuous probability distributions in the future. All right. So continuous data usually requires intervals. Intervals usually have an endpoint, a lower endpoint, and an upper endpoint. They're called boundary points sometimes. These are just giving other examples of data that is continuous that would warrant that we establish an interval for which to include it. Okay. All right. Variables and the data we assign to them have different levels of measurement scales. All right, from very basic to very advanced. And the first level of measurement is called the nominal level of measurement. Okay. Or data could have the ordinal level of measurement, or the interval level of measurement, or the ratio level of measurement. The way I remember these is I put an acronym to these. No IR, that's how I always remember this, is no IR. It's an easy way to remember this here. Nominal, ordinal, interval, ratio, no IR. Okay? Maybe that'll stick in your mind. That's a good way to remember this. All right, so what's nominal? Nominal level of measurement is the most basic level of measurement, or the most simple, if you will. It classifies data into mutually exclusive, which means non-overlapping categories in which order has no meaning, okay, or no relevance. For instance, a person's favorite color would be a nominal level of measurement. If I throw out the basic colors of red, blue, and let's say yellow, if I order those colors, is there any significance to ordering those colors? If I say blue, red, or yellow, red, blue, or do you think there's any significance to the ordering? Probably what? Probably not. Do you agree? Okay. So order has no meaning with nominal level of data. All right. The next slightly more sophisticated level of measurement is called the ordinal level. It classifies data into categories that can be ranked. And so rankings have meaning now. However, precise differences between ranks do not exist. An example, ladies and gentlemen, of ordinal level of measurement would be the place that a person finishes in a race, whether they finish in first place, second place, or third place. Ranks have meaning here. First place is a better rank than second place, is a better rank than third place. But the exact numerical difference between these rankings doesn't have any real meaning. Another example would be like letter grades. Receiving a grade of an A or a B or a C or a D or an F, okay? These grades can be ranked, and ranking has meaning, and yet we don't really know the exact numerical difference between these grades. That's called the ordinal level of measurement. Interval level measurement is more sophisticated. Interval level measurement always pertains to numeric data, where ranks have meaning, and ladies and gentlemen, there are actually very precise numerical differences between adjacent data points, which do have meaning then. The thing with interval level of measurement or data is that it does not have an absolute zero starting place, okay? For instance, temperatures on the Fahrenheit scale, all right? 20 degrees, or excuse me, 80 degrees compared to 60 degrees Fahrenheit. Okay, 80 degrees Fahrenheit is 20 degrees warmer than 60 degrees. So the difference between those two temperature values does have meaning. And obviously we can rank those temperatures from smallest to largest. But I have a question for you. Is there such a thing as an absolute zero on the Fahrenheit scale? Is there such a temperature as 0 degrees Fahrenheit? Anybody? 0 degrees Fahrenheit. You ever hear of it?
Yes.
Yes. But are there any temperatures lower than 0 degrees Fahrenheit?
Yes.
Yes.
Negative degrees, right? Negative 30 degrees, negative 35 degrees. And so, ladies and gentlemen, the problem with interval level measurement in the Fahrenheit temperature scale is that it does not have an absolute zero value where, you know, that is a rock bottom value, which below there exists no more temperatures on the Fahrenheit scale. It doesn't have that. All right. All right. Now, finally, the ratio level of measurement, which is the highest level of measurement. Ratio level data or variables possess all of the other attributes that the previous ones possess. In other words, order has meaning. Numerical differences exist and have meaning between adjacent data points. And, ladies and gentlemen, there's actually an absolute zero value for ratio level measurements. There's an actual absolute zero value. All right. For instance, weight, let's say the weight of a person would be a ratio level measurement or data value in the sense that, 150 pounds is, 30 pounds heavier than 120 pounds. So the differences have meaning. We can rank weights from smallest to largest. And unlike the interval level of measurement, weights would actually have an absolute zero value, meaning 0 pounds would be the absolute zero or the minimum value that any weight could ever achieve. Does that make sense? So do we see the difference between interval versus ratio? The main difference is what? Interval does not have an absolute zero value, but ratio does. Okay. I have a question. How about temperatures in the Kelvin scale? Kelvin, any of you scientists out there, have you ever had a course in chemistry or physics? Anybody know anything about the Kelvin scale? Does that have an absolute zero value?
Yes.
Yes, it does. It's called absolute zero, ladies and gentlemen, 0 Kelvin. And that is the coldest that anything could ever become. All right. In fact, there is a law in thermodynamics, though, don't tell anybody, that says that absolute 0 Kelvin cannot not actually be reached. Because to reach absolute 0 Kelvin, you would have to have a heat sink around that object that has a temperature that's lower than 0 Kelvin to draw off any heat so you could get down to 0 Kelvin. But there's a law in thermodynamics that says that there is no temperature colder than 0 Kelvin. Now, scientists have gotten very darn close in the lab to 0 Kelvin. Very, very close. But generally speaking, we say, yes, there is an absolute zero value on the Kelvin scale. It's called 0 Kelvin. All right, so ladies and gentlemen, what do you think about these right here? Zip codes. What kind of level of measurement do you think zip codes would be? Would it be nominal, ordinal, interval, or ratio? What would be your guess? Zip codes.
Nominal?
Well, yeah, they are numeric, and this is one of the few instances where a nominal data set is actually numeric. Zip codes. They're numeric, but let me ask you this. Is there any meaning in ranking zip codes? Is there any meaning with that? None whatsoever. Is there any meaning in taking the difference between 2 zip codes to say, oh, your zip code is 20 more than mine? There's no meaning in that. All right. So it's nominal. All right. Order makes no sense. There's no differences. Okay. You can't rank the values. There's no meaning. There's no absolute 0 zip code value. That doesn't have any meaning. All right. How about this next one here? Pizza size. Do you think that is nominal, ordinal, interval, or ratio? Pizza size. Can you at least order pizza sizes? Small, medium, and large?
Yes.
Yes, you can. Order does have meaning. Can you actually compute the numerical difference between a large and a medium pizza?
No.
I don't know what that even means. I never heard of such a thing. So it's probably at best It is nominal. You can order it, correct? Order has meaning. So I would probably stop short in saying it's ordinal level of data. That's about it. How about SAT scores? Well, SAT scores are numeric. Can we order them or rank them? Yes. Do differences between SAT scores take on meaning? Yes. Is there an absolute zero value for an SAT score? I don't know. I've never really seen one. So I'd probably stop short at calling this data interval level data interval. Okay. How about age of a person? It's numeric. Rank has meaning. Order has meaning. Differences between ages have meaning. Is there an absolute zero value for age? Can somebody be younger than 0 years old?
Yes. No.
All right. Now, I mean, we could argue this to the end of time if you want to get extremely detailed, but for all intents and purposes, ladies and gentlemen, we say that our age starts at 0. Okay. So this would be ratio level. Any questions about these levels of data here? Here's some more examples as to what type of level of data they would be here: color, zip code, letter grade, ACT, height, age, temperatures, Fahrenheit. Okay. All right. Again, I will be posting these, lectures on Canvas for your viewing. Okay, let's see here. All right, I'm going to try to get through these lectures first, and then anytime we have left, I want to try to do a couple problems out of your textbook. I'm trying to gauge the time, so I'm being careful here. All right. In lesson 1.3, we're going to look at 4 different ways of sampling or drawing a sample from a population. There's 4 main ways of sampling from a population. There's random samplings, or simple random sampling, as it's sometimes referred to. You might see it coined in a statistics textbook as SRS. That stands for simple random sampling. SRS. Systematic sampling, stratified sampling, and cluster sampling. These are very popular ways of sampling from a parent population to ensure that we have an unbiased sample, which is a good representative sample of the population. The key in sampling, again, is you need to guard against what's called bias. Bias is drawing a sample from a population that really does not represent in its entirety the population. Okay. All right. A random sample or a simple random sample is one in which is chosen from a parent population in which every element of the population has an equal chance of being selected. So when every element, ladies and gentlemen, of a population has an equal chance of being selected, when we reach in and pull out a random sample from that population, we call that random sample a simple random sample. Okay. Any of you play bingo? They got balls bouncing around in an urn or a container, and they draw a ball at random out of the lot. Do you agree that would be simple random sampling? A good example? Bingo balls?
Yes.
All right. What's systematic sampling? Systematic sampling is often employed in industrial quality control. For instance, if you have a machine that is basically manufacturing, let's say, widgets, you fill in the details as to what a widget is. It's turning out widgets all day long. Oftentimes, we like to sample every kth widget from the machine to make sure that it's within specs, whatever the spec requirement is for the particular part being machined. All right. That's called systematic sampling. For instance, if I sample every 10th bolt that comes off a machine, every 10th bolt, that's called systematic sampling. Maybe I'm measuring, let's say, the diameter, the cross-sectional diameter of a bolt, or its length, or maybe its girth, okay? And I select every 20th bolt that comes off the machine. That's called systematic sampling. All right. Stratified sampling involves, first of all, taking the population and subdividing it into stratums, okay, or into subgroups. And then reaching into each stratum or subgroup and pulling out a simple random sample from each stratum or subgroup. For instance, suppose that a state, ladies and gentlemen, is broken down into precincts. And let's suppose that I wanted to draw a simple random sample of 100 voters from each precinct. That's an example of stratified sampling. Or if you take a population, you break it down into 3 age groups. And then you pull out a simple random sample from each of the 3 age groups. That's called stratified sampling. Do you think that stratified sampling would tend to minimize bias? Anybody?
Yes, I think it sounds more specific.
It does a good job, doesn't it? Yeah, I mean, because we're subdividing the population into separate groups, so we're involving the entire population because we draw a simple random sample from each of the subgroups. So it's not like we're, isolating only one subgroup and drawing only from that one subgroup. So yeah, stratified sampling appears to be a very low biased way of sampling from a population. All right, another popular method is called cluster sampling. Cluster sampling, like stratified sampling, takes the population and basically subdivides it into smaller subgroups. But here's the difference. With cluster sampling, once we subdivide the population into smaller subgroups, we randomly choose a few of the subgroups. And then we basically poll or sample every element in the randomly selected clusters. Okay. An example would be this. Again, if I had a state and I subdivided the state into all voting precincts, let's say there were like, 50 voting precincts in a state. Let's say I randomly chose precincts 11, 35, and maybe 49. That's called drawing a cluster sample. And then I would poll everybody in precinct 11, poll everybody in precinct 35, and poll everybody in precinct 49. That's called a cluster sample. Do we understand the difference between stratified versus cluster sampling? They have similarities, but there is a difference. Do we understand the difference?
Yes.
Good on that?
Is
Okay.
there more of a chance for bias in a cluster sample than would be a stratified sample?
It seems like there might be. It depends what your population is all about too, okay? The cluster sampling, you got to admit, is still pretty decent in the sense that, here's why it's still decent. Because every cluster has an equal chance of being selected. Do you agree? If we choose a simple random sample of clusters, do you agree that every cluster would have an equal chance of being selected?
Yeah.
Yes.
That is a good thing.
Yeah.
You see, the more randomization, ladies and gentlemen, that you can inject in your sampling, the more randomization, okay, the less sampling error you're going to incur. All right. Here's a big notorious way of sampling, convenience sampling. Suppose, ladies and gentlemen, that I wanted to poll, let's say, auto workers on a particular issue, okay? Suppose that I stand only outside the door of blue-collar workers, and as they file out at the end of the day, I poll each one. That's called convenience sampling because that's an easy sample for me to collect. I just sit there at that entrance and just poll as the people walk out. But do you agree that there is some bias in my sample? Do you think that's a good representative sample of the entire company's employees?
No.
No, I'm only polling out of convenience, only a certain sector of the population. Okay, so convenience sampling, although it is convenient for the one collecting the data, is usually plagued with bias. Stay away from convenience sampling. Okay. Here's another faulty way of collecting data, volunteer or self-selected samples. Volunteer sampling, ladies and gentlemen, has a big problem with it because usually it only attracts people that are interested in a particular issue. Okay. But does that mean that you're going to get accurate results and a good representation of the mindset of the entire population if you conduct volunteer sampling? Probably not, because even though a large sector of your population chooses not to, undergo the interview, if you will, that doesn't mean they don't have a mindset, or they don't have any certain opinion about a particular issue. It's just that they choose to stay out of the sample and out of the investigation. That injects bias. Okay, so be careful with volunteer and convenience sampling. Try to stay away from that. The more randomization you can conduct in sampling, the better results you're going to be, and the less sampling area you're going to incur. Okay. All right. Whoops. Wrong one. All right, last section here, 1.4. All right, hopefully we can explain the difference between observational and experimental study and explain how statistics can be used and misused. All right. And that is a very big problem with statistics, is that data can be fabricated, or it can be basically fudged to paint any picture that you want it to paint. But that doesn't mean it's doing any justice to the numbers. Okay, so if nothing else, hopefully we learn, ladies and gentlemen, when we work with data, that we bring along something called integrity. Okay, when working with data, we don't throw out data points. All right, we don't create data points. Data is data. All right, data doesn't lie. The only thing that injects bias and lies are people, humans. All right, and some people are serving time because of fudging the data. All right. All right, ladies and gentlemen, what's an observational study? An observational study basically is where a researcher takes a hands-off approach to the investigation. Basically just sits back and just records results. Okay. The nice thing about an observational study is that basically you are immersing yourself in the natural habitat of what it is you're studying. And so that your results will not be under any duress, okay, because of change of situation or change of location. All right. For instance, an observational study might be, observing traffic at a busy intersection. Maybe recording how many cars enter and exit the intersection on an hourly basis. That's an observational study. All right. Again, observational studies are nice. Like if you're going to observe, let's say, the offspring of like a great white shark. You'd want to go out where the great white sharks live naturally and then observe their nature and maybe their breeding habits in the wild. That's called an observational study. Again, it's a hands-off approach. We don't actually go in like with the great white sharks. We're not going to go in. We're not going to, we're not going to necessarily go down in a submarine. We're not going to, tether ourselves to the shark and follow the shark around. That's not an observational study. We basically observe them in their natural, undisturbed habitat. All right. Now, sometimes observational studies, ladies and gentlemen, are not really practical. For instance, if you're trying to study murder or suicide, you're not going to stand there or sit there and watch somebody kill themselves or commit suicide. It's considered to be unethical, right? So that's not very practical in that situation, right? So observational studies do have limits. Here's some problems or some cons with the observational study method. We don't really have control over what it is we're observing. And because we don't have control, all right, oftentimes the data we collect may not conform to our desire, all right? And it might be difficult to establish any sort of cause and effect relationship when just observing something in its natural element, right? Sometimes it's very difficult to go to where it is you want to observe a particular phenomenon. That's another drawback. Observational studies often are studies conducted by maybe third-party people or people that don't really have an invested interest or might be biased in some way, shape, or form. And who knows, maybe they'll fudge the data and then turn it over to you, and you have a fudged, biased data set. So there are some flaws with the observational way of doing things. All right, let's contrast that now with another way of conducting a study called experimental. In an experimental study, this is where a researcher takes a more active role, ladies and gentlemen, in studying its subjects, okay? For instance, if we want to study the effect of a new drug on maybe curing a particular ailment, what we might do is we may randomly distribute a placebo pill. That is basically a pill that does not contain the medication under study. It's like a sugar pill. We may randomly, distribute a placebo pill to our subjects, and we will randomly, distribute the pill that actually contains the real medication that's being studied. Because we're actually interjecting ourselves amongst our subjects, ladies and gentlemen, actually allocating these pills, albeit in a random fashion, this is considered to be more of an experimental type study because we're taking an active role, okay? When we conduct an experimental study, oftentimes we have to clearly define what is called an independent variable, or sometimes referred to as an explanatory variable. In algebra, when we're working with equations in two variables, we normally call the x variable the explanatory or the independent variable. The dependent or the outcome variable is often referred to as the y variable. And we will see this come to fruition when we get into regression and correlation analysis. X will be the independent variable, y will be the dependent variable. All right. So the nice thing about an experimental study is we have more control over the situation. We can basically hold fixed all other variables and only allow one independent variable to change to see what type of effect it has on one independent variable, okay? Because we have all this control, ladies and gentlemen, we can get more accurate results than maybe an observational study. But this requires that we interject and interact more so with the actual subjects under study. And so this is definitely not an observational study because we are controlling the variables that we want to control, hold fixed, and we're only allowing certain variables to vary in order to see what's going on with the dependent variable there. All right. And again, when we are conducting an experimental study, like with the drug versus the placebo pill, we have a treatment group. That's the group that receives the actual drug, and the control group is the group that receives what is called the placebo. All right. So we do have some control as to who receives what, and that's why it's called an experimental type study there. All right. And here are the advantages that I already basically stated. We do have a lot more control in experimental studies. That's a major advantage. Okay. Disadvantages of an experimental study. You could have what's called a Hawthorne effect, ladies and gentlemen, or sometimes it's referred to as the placebo effect. For instance, if you were part of a study and you knew you received the pill that has the actual medication on board to maybe, let's say, reduce the duration of a cold, you might be, okay, duped into thinking that, well, because I know I received the medicated pill, that I should start to feel better. So your mind might actually start to convince yourself that you do feel better, when in fact, maybe you don't, because you know that you received the medicated pill. This is called the Hawthorne effect or the placebo effect. That's the problem with an experimental study, all right? That's why it's critical to perform what's called a blinded study. That is, you don't want your subjects to know whether they receive the medicated pill versus the placebo. You don't want them to know. All right. If you only know, but your subjects don't know, that's called single blinding. If you, the researcher, don't know and your subjects don't know what pill they received, that's called double blinding. Okay. A double blinded experiment. But don't get me wrong. Somebody has to know who received the placebo versus the medicated pill. All right. But blinding is a good way to reduce bias when you conduct an experiment. Whether you blind your subjects to what they received, let's say with the pill, or you blind the subjects and the researcher. Double blinding, that can reduce bias. Another big problem is confounding variables. Confounding variables are variables that, how shall I say it? They're extremely similar to the independent variable you're trying to study. So much so, ladies and gentlemen, that it's extremely difficult, if not impossible, to weed out or separate the confounding variable from the actual independent variable you want to study, so as to hold them constant and fixed, so as to only see the effect between the variable, the independent variable you want to study, versus the dependent variable and the effect it would incur from the variable that you want to vary or allow to vary. So confounding variables can seep into an investigation. You really got to guard against those. For instance, if you put subjects on an exercise program, and also change their diet or engage in other healthier habits, the problem is, ladies and gentlemen, how do we know that any improvements in their health is attributed to exercise? There's a possibility that any improvement in their health could be attributed to some of those other confounding variables that we failed to what? Hold constant, such as diet or engaging in other healthier habits. All right. So sometimes, and healthier habits would include exercise. So it's kind of like those are like inseparable. So sometimes it's very difficult to, okay, weed out or separate from the variable that you want to study other variables in order to hold them constant. Those are called confounding variables. That can inject bias into your investigation. All right. Misuses and abuses of statistics. It happens all the time, every day, unfortunately. Statistics is abused every day. For instance, if you're trying to conduct an investigation with data without any comparison, that can be very deceptive. To make a conjecture and say this product has 20% less fat, and you don't compare it with something else, okay, then we're at a loss as to 20% less fat than what, okay? And that can be very deceiving. 20% less fat than what? Compared to what? All right. Being very general in your statement or conclusion involving an investigation can cause problems. For instance, saying like a breakfast cereal may help prevent heart disease. May help prevent heart disease. That don't sound too conclusive or too scientific to me if you say may help. How do you know that for sure? Okay. Graphs are always notoriously known for misleading investigators, and I'm going to show you a couple of those in a second. All right. Survey questions, ladies and gentlemen, can be posed as biased questions from the researcher. For instance, if you're hoping that a population answers a certain way so as to convince another party, you might design the survey questions so as to basically deceive your subjects into answering the way you want them to answer. That can be bias in problems, okay? All right. I want to take you now to another textbook. This is another stats book that has something I want to show you. Wrong website. Here we go. Not here. Okay, here we go. Okay, graphs can be very misleading. All right, I want to show you a couple of these here. All right, ladies and gentlemen, here are two graphs, bar graphs, okay, that basically pertain to passenger traffic at the Denver International Airport for various years, 2009 through 2015, and millions of passengers. All right, now, which graph appears to show that there's a huge difference in the passenger volume versus years? The top graph or the bottom graph? Which one?
Bottom.
The bottom one. It makes it look like there's a huge difference between 2009 and 2010. Do you agree? Now, let's compare this graph with the one above. Huh. For 2009 versus 2010, it doesn't look like there's hardly any difference. Do you agree? Which graph is the misleading graph, the top or the bottom one? Anybody?
The bottom one.
The bottom one.
Bottom.
Why is it highly misleading? I'll give you a hint. Look at the vertical axis, the y-axis. What does the bottom graph not have that the top one does have?
Top one starts at 0. The bottom one starts at 50.
There you go. Ladies and gentlemen, you got to be very careful when you're designing bar graphs or histograms. If your vertical axis does not start at 0, okay, but starts at some other non-zero value, you can be falsely led into believing something that is not true at all just by glancing at the graph. Be very careful. Make sure your vertical axis always starts with 0. All right. You can see there's a huge difference here. All right. Be careful of that. All right. This is passenger traffic at the same airport for the same years. This is a line graph. Okay. Now, the top line graph doesn't look like there's much change. The bottom line graph looks like there's radical change. Which graph is misleading? Top line graph or bottom line graph?
Bottom.
Bottom one is in big error here. There's no 0 on the vertical axis. And because of that, it looks like we have inflated changes between these years of passenger volume. Again, ladies and gentlemen, use 0 on the vertical axis. You can see there's a huge difference here if you're not paying attention to the scales. All right. Cost of jet fuel. This is a bar graph that indicates the differences in cost of jet fuel between 2 years, 2012 and 2016. And it looks like that there is a difference. This is cost per gallon in dollars. 2012, the cost, I would imagine this is maybe average cost, $3 per gallon versus 2016 looks like about $1 a gallon here, okay? Suppose we portrayed this data set using these pictures of airplanes. Pictures of airplanes. Ladies and gentlemen, with the data that we have in the bar graph, there's only what? A $2 difference. Do you agree? Between the cost of 2012 and 2016 jet fuel. If I didn't give you that bar graph, just gave you this picture, what's wrong with the picture? Anybody? If the size of the plane is proportional to the cost of jet fuel, what's the problem with this picture?
You would think the 2012 one took a lot more gas than the 2016.
Yeah, a lot more. I mean, not just $2 more, a lot more. Do you agree? This picture is much larger in size than this picture here. That is highly misleading. Unfortunately, newspapers are notoriously known for watering down statistics for the lay people so that they can just try to appreciate and cut through the chase of the numbers. But you got to be careful. You want to scrutinize this diagram here, ladies, before you make an accurate determination in your mind as to what it's saying. All right? Try to be more accurate and be a little bit more judicious when you're looking at graphs as to the validity and the accuracy of these graphs here. All right. All right, let's see here. Problem number 5. Again, what's plaguing these bar graphs is one has 0 on the vertical axis versus the other one does what? Does not, correct? Again, always use 0 on your vertical axes. Let's see what number 6 is all about here. This line graph is suffering from the fact that the vertical axis is missing also what? 0, correct? And so that it looks like it gives you a more inflated rate of change of millions of dollars versus time, whereas the bar graph does better justice in what's really going on there. Again, pictures can be very misleading. The size of this dollar below versus the size of the dollar above can have you misled into believing that there is a huge difference between 2016 and 2008, when in fact, there's not that big of a difference. Only a $12,000 difference. Okay. So pictures, again, sizes of pictures can be misleading. Be careful with that. All right. Three-dimensional graphs can be misleading because it's very difficult to see exactly where the top of the bar is. Right? If they got them in 3D here, it's kind of like you almost have to project it to the background, but that's work. You shouldn't have to do that kind of work. So 3D graphs look pretty and everything, but they can be misleading. All right. So those are some problem areas with graphs and pictures and things. All right. Now, let's see. I wanted to go to Alex. I wanted to go to the textbook if I could. So I'm going to go get the e-textbook here. I just wanted to do a couple of problems out of here if I could. We don't have much time left. Let's see here, section 1.2. This is how you click on the table of contents up here, these little horizontal bars, and then you can navigate very quickly to the section of interest here. I want to go to section 2.1, oh, excuse me, 1.2. All right. And I want to go down to a couple of problems here in your actual homework section here. All right. Problem number 5. Determine whether the data is qualitative or quantitative. The number of stores a person visits on a shopping trip. Do you think that's quantitative or qualitative?
Quantitative.
Quantitative, you got it. Yep, makes sense. All right. All right. Let's see here. Number 9, the number of degrees awarded by a college each year for the last 10 years. Probably what?
Quantitative.
Quantitative. Okay. All right. So we good on that, ladies and gentlemen? All right, let's move on. Section 1.3. Couple problems I want to look at here. Problem 11 through 16. Identify the sampling method that was used. Number 11. A machine fills bags of apple slices for sale to customers who eat at a fast food restaurant. To check the accuracy of the weight of the bags, every 10th bag is selected and weighed on a scale. What method of sampling is that? Anybody? Is it simple random sampling? Is it systematic sampling, stratified sampling, or cluster sampling? What would be your guess?
Systematic sampling.
Yeah, it's systematic sampling because you're choosing every 10th bag. You're only polling every 10th bag. That's systematic all the way. All right. Number 12, what would be your thought? To determine how long people exercise, a researcher interviews 5 people selected from a yoga class, 5 people selected from a weightlifting class, and 5 people selected from an aerobics class, and 5 people from the swimming class. What type of sampling would you think that this might be?
Stratified.
Yeah, they're taking all the different types of exercises that, the most popular exercises, they're saying we're kind of like breaking it into like subgroups, aren't they? Yoga, weightlifting, aerobics, swimming. And looks like they're selecting 5 people. It doesn't say at random. It does not say at random. But it doesn't say they're polling everybody in the classes that were selected. I would probably lean towards stratified there. Okay. All right. Number 13, a fast food restaurant is selected at random. Then the times it takes to fill customers' orders are recorded. These results are used for a commercial for the restaurant chain. What would be your guess? A fast food restaurant is selected at random.
Random sampling.
Simple random sampling. Well, I will give you this. It looks like they're simple random sampling everybody at the selected restaurant. They simply random select the restaurant among many restaurants in a chain, though, which means that every restaurant in that chain had an equal chance of being selected. Do you agree? What do you think? Anybody think any differently on this one? Instead of just simple random sampling?
Is it cluster sampling?
Yeah, it could maybe be cluster sampling. I could see where you could argue it that way too, because you're dividing the entire population of these restaurants up into different, many different restaurants. Okay, you're breaking them up into clusters. You're randomly then selecting one of your cluster or one of your restaurants, and then you're polling everybody at that restaurant. Let's see what the answer says here. Well, it says cluster, but in a way, ladies and gentlemen, I can kind of understand and see when you said simple random sampling, that does have some justice to it also. So this is one of those questions in statistics, one of the few questions whereby you have a little bit of a gray area. Fortunately, most problems in statistics are clear cut and dry. Okay. All right. So we're done with that one there. And let's see here. All right, let's see if we can try maybe another one here. Number 16, 10 counties in Pennsylvania are randomly selected to determine the average county real estate tax that the residents pay. What do you think? Number 16. Let me ask you this question here. Obviously, Pennsylvania has probably more than 10 counties. And so the whole state has been basically subdivided up into counties, correct? So this really has, features which are inherent for stratified sampling and cluster sampling. What's the difference? What else would differentiate between cluster and stratified sampling in this reading here? So that we know which one to choose. So far, in the early going, it looks like it's both stratified and cluster, but we got to select only one.
Wouldn't it be cluster because it was at random and not a certain subgroup?
Okay. Yes, cluster for many reasons. For one thing, we randomly selected these 10 counties of all the counties in the entire state, which means each county had an equal chance of being selected. Number two, to compute the average real estate taxes for the entire county, do you agree you would have to poll everybody in that county? Isn't that true? Or you'd want to poll everybody in that county to compute the average real estate taxes for that county? It really sounds like this is cluster sampling for those two reasons. All right. All right, let's move on out of this. Let's see what else we got here. 1.4. Okay, let's go on down. See what we can get into in here, down here. This is section 1.4. Couple of problems in here. 15 through 18, determine whether an observational study or an experimental study was used. Number 15, a group of teachers are asked if they believe that social media and texting are bad for the grammar and spelling of their students. Do you think this would be an observational study or experimental?
Observational.
Yeah, I would be, if I had to lean towards one or the other, I'd be going observational myself, because it doesn't really look like the teachers are, let's say dividing up their classes into different groups. Like, you can use social media during class, and this group you cannot. Okay, I don't see any of that going on. I'd be leaning towards observational, and that's what they're agreeing on. All right. Number 16, two groups of college students are randomly selected. One group is shown a promotional video on purchasing life insurance after they graduate. The other group is not shown the video. After this, each group is asked if they are planning to purchase life insurance after they graduate. What would be your guess? Experimental type study or observational?
Experimental.
Why do you say that?
Experimental.
And why do you say experimental?
One group is shown one and the other one isn't shown the video. So
That's
one's
right.
one's the experimental group.
That's right. The researcher, the investigator, is actually taking an active role in separating these groups and having only one group view the video and the other group not viewing the video. Because the researcher is taking an active role, ladies and gentlemen, we kind of have like a control group, versus the other group. And because of that, this sounds experimental all the way, right? Because we have control over who's been allocated to each group and who receives the video versus doesn't. Number 17, a researcher wishes to see if there is a difference between the times that a physician spends on virtual visits and in-person visits with patients. They're not really giving us many details as to how this study was conducted, or so we're kind of at a loss on some of these, you got to admit. Virtual versus in-person visits. What would be your guess if you had to guess? Observational or experimental?
Observational.
I would probably lean that way myself, because it just doesn't look like there's any interjection where the researcher is taking an active role and allocating a group of doctors to one situation versus another. I don't see any of that going on here. It looks like we're just taking observations of a doctor in their natural settings on a day-to-day basis. I would think observational. All right. Okay, 19 through 22, it says identify the independent variable and the dependent variable. Number 19, a study was done to see if people who run regularly at least 3 times a week are more likely to have lower blood pressure than those who walk regularly at least 3 times a week. I have a question for you, ladies and gentlemen. What would you let the independent or the explanatory variable x be equal to? And what would you let the dependent variable y be equal to in this study? What do you think? I want to try to draw a cause and effect relationship between x and y. So what would you allocate as being x? Independent variable. In other words, what variable is kind of a cause for the other one? Think of it that way.
How many times they run?
Yes, there you go. I would let x be equal to the number of times, the number of runs that they conduct on a weekly basis. That's what I would do. Then what would be y, the dependent variable? What would depend upon the number of times a person runs? Think about it.
Blood pressure.
Blood pressure. The y, the dependent variable, would be the blood pressure. You got it. Does that make sense here? How we differentiated between the independent versus the dependent variable there? Okay. All right. Let's try another one here. Number 20, the Journal of Behavioral Medicine reported that sharing a hug and holding hands can limit the physical effects of stress, such as soaring heart rate, and an elevated blood pressure. What would you tend to let X be equal to versus Y be equal to? Anybody? What would X be? What would you be tempted to let X be equal to and Y to be equal to in this? If you were to arrange a study here. First of all, do we even know we're trying to draw an association between? Trying to draw whether or not there's an association or relationship between hugging and holding hands versus the what? The level of
Stress.
stress, maybe? So what would you want to let X be equal to, the independent variable? What do you think?
The hugs.
Yeah. X would probably be the number of hugs and or the number of times you hold hands. Y would be the dependent variable that depends upon that, which would probably be the what? The level of stress. Now, how would you actually measure level of stress as a numeric value? Well, you would probably maybe measure it as the what? The heart rate per minute, or maybe the blood pressure reading. Those are numeric ratio level data values. Do you agree? Ratio level. How about number 21? People who have obsessive compulsive behaviors are likely to be perfectionists. What would you let X be equal to there? What would Y be? Well, this one's a tough one. Let's see. Obsessive compulsive behaviors. How would you even quantify these things? You know what I'm saying?
So would it be like perfectionists versus compulsive behavior and where they meet?
It kind of seems like that's the way you would go. Y for perfectionist, X for what? Compulsive behaviors. Boy, wouldn't it? My question is, how would you even quantify and collect this data as an ordered paired data set? I mean, how would you even quantify obsessive compulsive behaviors? How would you do that? And how would you quantify being a perfectionist or not? That's a very good question. We don't have to answer those questions, by the way. This is not about that. But, that just kind of lurked into my mind. Wouldn't it be kind of difficult, do you think, to quantify these variables? I just thought they'd be kind of difficult. All right. All right, let's see. Okay. All right, so ladies and gentlemen, we did not really have any classwork this time. That will be changing in the future. Like I said, our future lectures are going to become more quantitative and more computative in the future. So this is kind of a rarity here, this early lecture. Make sure you do bring your calculator to all future class sessions. And again, something to write on and something to write with, as we will have little classworks that I will want you to do during class and email to me by midnight of that day. But there is no classwork. You have to email to me by midnight tonight. I'm going to let you go, and you have a good day, and hopefully I'll see you in a couple of days. I will post this PowerPoint presentation on Canvas. Okay, the sections 1 through 14. I eventually will be opening up some homework problems on Alex for these sections. And so just make sure that when the homework assignments become available that you don't procrastinate. The worst thing you can do in a computative course is get behind. All right, never get behind in a computative course. So try to stay up with it as the course goes on. And that way you'll minimize the amount of stress and maximize the potential good that can come from this course. All right, ladies and gentlemen, you have a good day. I'm going to let you go. If you have any lingering questions, you can stay on the line, as I will stay on the line for a couple of minutes to answer any questions you have. Other than that, have a good couple of days. I'll see you on Thursday, hopefully. All right. Wait, no, I'll see you next week. I'm sorry. You have a good weekend. All right, I'll be on the line for a couple of minutes.
Have a good day.
See you. All right, the first homework, when will it actually be available? I don't know. It might not be available till tomorrow or something. Okay. Yeah, I gotta look at the screen problems and everything. Yeah, go ahead.
Oh, I had a question. It was just on the rubric where you have like when everything's due. I noticed that like for chapter 1 and 2, it doesn't show the due date for the quizzes
Second, let me
for
show
those.
you.
Or
What's going on now? For what now?
for chapter 1 and 2. Like you see how you have like the quiz due? Like I don't like it's no quiz due.
Oh, you mean for a chapter 1 and 2 quiz?
Yeah,
Hmm. You know, I don't have a chapter 1 and 2 quiz, do I?
yeah.
Yeah,
So
I noticed that when I was going over the schedule. It's like, what? Why did I omit quizzes from those chapters there? Um, I may create quizzes for these chapters, and if I do, I'll let you know via email. I'll let
okay.
you, and I'll also make the change on the schedule, okay?
Okay.
But I'm going to
Thank
think
you.
about that, all right?
Okay, thank you.
All right, you have a good day.
You too.